So today is a really important, super important day in calculus. Today we're going to combine our big ideas. So remember way back to the beginning of class, we had two big problems we wanted to solve. First, we wanted to figure out how to compute area along curvy lines, and we also wanted to figure out speed, rate of change, the slope along curvy lines. And in order to solve these two problems, we introduced the ideas of an integral and a derivative, and they didn't seem to have much in common except that they did involve limits. And so even though we defined an integral in terms of a limit and a derivative in terms of a limit, as it turns out there is another connection we're going to make between integrals and derivatives today. We're going to see that they're actually connected more than just limits are used in them. There is actually a really strong connection between these two ideas. And so at the top you'll want to notice we have definitely a good number of keywords to look at today. There are actually going to be a lot of vocab words in this section. It's just the way it is. But we'll see that a lot of them are familiar and a lot of them will go together quite well. So let's recall and think back to our definite integral here from a to b of the function f of x dx. And think that this really does depend on the two letters a and b. So if we remember geometrically, as long as we had a positive function like we have here, what we can do is we can look at where a is and we can look at where b is. And this just means, find this area in between. But it really depends on what we pick for a and b. If instead we decided that, well, if instead we were going to compute the integral from, say, alpha to beta of f of x dx, so we picked different letters, alpha over here and beta over here, well, this is going to be a different area. And so it really does depend on what letters we choose. So what we're going to do is we're going to fix one of these and just think about the other one as a variable instead. So even though our integral originally had two things to think about, what we're going to do is we're going to fix the lower limit as a, we're going to denote the variable of integration by u instead of x, and we're going to denote the upper limit by x instead. And so this all comes together for this new function we're going to define. So this is the Greek letter phi, so phi of x will be the integral from a to x of the function f of u du. So the key is to make sure you think about this thing really as a function, and you can kind of think of it as a function that sort of picks up change. So for instance, if over here we start at a way over here, so a will be the same on both of these. But over here, say I went out to, let's just give it a number, 5. So this area in here represents the integral phi of 5 would give you this big area. Whereas if I picked a number, say, let's call it 7, phi of 7 represents this bigger area, this bigger change. So this thing, it still really is a function. It still depends on what value you put in for x. And that x just tells you how far to integrate. It tells you where to stop your integration instead. And we're going to call this function phi of x an indefinite integral. So it's very important here to think about this word. It's an indefinite integral of the function. So these articles are important here. I used the word an indefinite integral. I didn't say the indefinite integral, right? When we talked about derivatives, a function has the derivative, but here we just have an. So let's talk a little bit more about that. So what I could have done is I could have chosen a different value for the lower limit of integration. I could have chosen alpha here instead, and I would have ended up with a different function. So let's compare these two and see how they look differently. So geometrically, if we look at what these functions mean, well, the key features is that they're both going to stop at some value, let's call it x over here. However, the function psi over here starts at some value alpha, and so what it's saying to do is it's saying to take and compute the area over from alpha all the way up and stop at x there. So it's this green area. Whereas the function phi here, instead what it starts to do is it starts over at some number a instead, so that's a nice little a, and it says instead compute this area instead. So we can see that these are really different functions. Even if you put the same x value into them, you're going to get different numbers out. So these functions do have different areas, so that's why we say an indefinite integral. There are multiple choices you can make here for your starting lower bound of integration, alpha, a, 1, 2, any number you want. But what's interesting here is even though they're different, their difference is going to be just a constant. It's just going to be a number. This area in here between alpha and a is their difference. So what we can see is, though, even though we put different numbers in there, that number we get out is actually going to be a constant, and it'll actually always be the same constant, okay? It doesn't depend on x. X can be a million, x can be a billion. It doesn't matter what x value you choose way over here, you're always going to get the same difference between all these functions. So they're always going to differ by just some constant. So this idea is crucially important, okay? These two indefinite integrals, they're both indefinite integrals because you can just pick any number you want for alpha, for a, for your lower bound of integration. It doesn't matter. The key, though, is that they differ by a constant. They're only off by a little constant, some number. It's not some big function making them different. It's just some number. So now that we've built this new function called the indefinite integral, let's apply some calculus to it and let's try taking the derivative of it and see what happens. And as it turns out, something really neat happens when you take the derivative of an integral. What you get is you get what's called the second fundamental theorem of calculus. Now, it's a bit of a historical accident that this is called the second fundamental theorem of calculus, when really it is the most important theorem in calculus. Another one is more practical, more useful. We'll get to it later. But this really tells us everything there is to know about calculus in a nutshell. So it says, take yourself a nice continuous function that has a nice indefinite integral. So pick any one you want and try to take the derivative of it. Well, as it turns out, if you take the derivative of this indefinite integral, what you're going to get is that phi prime of x is equal to f of x, the function that you're taking the indefinite integral of. So what does this mean? This means that if you tried to take the derivative of the integral of this function, what you're going to get out is you're going to get the function that you started with. Now, this is amazing because this means that integrals and derivatives are inverses of each other. They undo each other. We've seen this before with simpler functions, addition and subtraction are inverses, multiplication and division. Well, as it turns out, derivatives and integrals are practically inverses of each other. The way to remember this is that the derivative of an indefinite integral of a continuous function equals that continuous function. So before we show some applications of this, let's think about, well, why in the world could this possibly be true? So the big key to this theorem is this statement right here that says that the derivative of the indefinite integral equals f of x. So that's what we want to prove. And we need to find the derivative, so we have to begin by setting up our difference quotient here. So our difference quotient will be phi of x plus h minus phi of x all over h. And we're going to move on and see what this means graphically. So we want to try and figure out a way to compute this difference quotient. And so what we're going to do is we're going to look at the graph. And we're going to start by looking at just the numerator part of our difference quotient. So the key feature is that phi of x plus h really means the integral from a to x plus h of f of u du. And phi of x means the integral from a to x of f of u du. And so we want to think, well, what does this mean graphically? Well, both of these integrals are going to start over here at some number a. And what they're going to do is they're going to go out, and there's eventually going to be a point x over here. And there's also going to be x plus h. And so what this first integral is telling us to do is it says, well, compute the area all the way out from a all the way over to x plus h here. And what the second integral, phi of x, we're going to subtract from it says to do is it says, well, start at a again, but stop once you get all the way over to x. And so what we can see is since we're subtracting them, we want to find their difference. And so what we're left with is we're going to be left with this integral from a to x plus h over here. So it's just going to be this area over here represents the difference between the green and the blue. And so really the numerator of this difference quotient is equal to this value right here, whatever this integral is. Now in order to figure out the integral between x and x plus h, what I want to do is I want to try to trap this region. So I'm going to let xg be the point on the interval from x to x plus h where f of x takes its greatest value. So if we look between x and x plus h, it looks like my greatest value is right around here. So I'm going to come down and grab at this point, this is going to be x of g. So I'm going to have x of g, because that's the point where I take my greatest value. In a very similar way, what I'm going to do is I'm going to pick a point on my interval, x sub l, where my function takes its least value. So if we look along this curve, I would say it takes its least value right around here, maybe near the point x. So x sub l is going to be this point, my least value on the interval. Now why have I done this? The reason I did this is because now I've trapped the area of the integral I want to compute between two different rectangles. So if I can look here, what I see is that h times f of x g means that I'm going to take this height at xg and I'm going to multiply it by the width of my interval. So I'm going to get a rectangle here with a certain area. I can do the same thing for xl. I can take the width of my interval multiplied by the height, and I've got another rectangle that approximates the area. And what it is the red rectangle is a lower approximation for the integral. The green rectangle is an upper approximation. And so what this does is this traps the actual area somewhere in between these two areas. Therefore, what I've done is I've trapped my numerator here in between these two other area computations. I've really trapped that integral right there. And so now we want to see what happens, though, once we start making h pretty small. So after dividing, what I'm going to get is I'm going to trap actually my difference quotient here in between these two other quantities. I'm going to trap it between the high value it takes on the interval, and I'm going to trap it between the low value that my function takes on the interval. And so now, of course, well, we want to compute the limit as h approaches 0, and so we want to think, well, what's going to happen on both sides? And so as h approaches 0, the high value on my interval must get closer to f of x, that point, because we're squeezing it on in. And also the lowest value on the interval must also get closer to f of x because it's continuous. They have to both, the high and the low point both have to slide on towards actually the value f of x, which means I've trapped my limit in between. So what we have then is that the derivative phi prime of x is equal to the limit as h approaches 0 of my difference quotient, which must equal f of x. And that occurs because both the upper part goes towards f of x and this lower part also goes towards f of x, so it gets trapped in the middle there. And so really this is exactly what my theorem states. This states that the derivative of the indefinite integral is equal to f of x. That is, taking the derivative of any indefinite integral f of u du is equal to f of x. Now the key thing here that's really amazing, this does not depend on a. Okay? A doesn't occur anywhere here. It doesn't matter. You could have picked any a that you wanted. You're going to get the same thing. The derivative of any indefinite integral equals f of x. And that's pretty neat. So I'm not going to let you go without saying this a lot. This was the pinnacle of mathematical achievement in the 1600s. It brought together the ideas of derivatives and slopes. It brought together integrals and areas. All together, and it's the reason why you have computers, cell phones, you name something pretty neat technology-wise that you have today, and it is pretty much a result of calculus. So next we want to talk about an idea called antiderivatives, and it seems a bit strange at first. I admit that it doesn't seem to fit with what we've just been doing, but I promise it's going to come back around. It seems like a tangent, good math joke, but it's going to make sense. So usually what I'll do is I'll give you a function and say find the derivative, okay, or compute the area or something like that. But what we can do is we can also ask the question a different way. We can say give me an example of a function f such that its derivative is 3x squared. Okay, so if you think about this for a little while, what you'll probably do is you'll probably think, well, 3x squared, that's a power function, so maybe something with a power rule. How am I going to get that 3 down front? I have the 2 up there. And hopefully after a little bit of trying, you say, well, hey, let's try the function x cubed. Because if we take x cubed, then what we can do is we can use the power rule. And the power rule says, well, the derivative of x cubed is 3x squared. You bring the 3 down in front, you subtract 1 from the exponent, you're good to go. And so, hey, we've solved the problem. And so what we're going to say is we're going to say generally a function f is an antiderivative of a function on an interval if the derivative of it is equal to the function f of x. So therefore in our case what we can say is we can say the function f of x cubed is an antiderivative of 3x squared. Since the derivative of x cubed is 3x squared, it's an antiderivative. Now I said the word an again, right? I didn't say the antiderivative. I said an antiderivative here. We have many choices, okay? We could have picked x cubed plus 5. If we take the derivative of this function, what we're going to end up with is we're going to end up with just 3x squared again, okay? Because the 5 is a constant. Take the derivative, it's 0. So super thing, and how this connects to the stuff we did before is that every indefinite integral of the function f of x is an antiderivative of f of x. That's what the theorem we just talked about tells us. In that previous theorem, we just showed that phi prime of x equals f of x, which means it is an antiderivative of f of x. But our very natural question to ask at this point is this all of the antiderivatives? Are there other ways to find them? Or, are we always just going to have to guess at them? Or is this indefinite integral, is that the way to go? How do we go about finding them all? So what we have here is a theorem that tells us how antiderivatives can look. So we say if f and g are both antiderivatives of a function, then if you subtract them, you're going to get a constant. Okay? Therefore, every antiderivative of f has the form f of x plus c, where c is a constant. So what this tells us really is something really pretty neat. What it tells us is that since capital F of x equals x cubed is an antiderivative of the function f of x equals 3x squared, this means all antiderivatives of f of x look like x cubed plus c some number. So this means all of them look like that. We don't need to go hunting very carefully for them. Pretty much once we've got one, we've got them all. So we can pretty easily see that f of x plus c is going to be an antiderivative of f of x for any constant we pick c. If we start and we just decide, hey, well, let's take the derivative here of f of x plus c, well, we remember some of our derivative rules we learned so far. I can break this up into two separate derivatives here. And then these are really easy derivatives to take. By definition, since capital F of x is an antiderivative of f of x, its derivative is just f of x. That's what an antiderivative means. Plus I get 0 here. And so, since the derivative of f of x plus c is equal to f of x, it's an antiderivative as well. So that part's not so bad. The other part isn't so bad either, that when we subtract the two of them, we get a constant. Because once again, all we have to do is we have to take their derivative. We say, well, let's consider a function h of x. So suppose we take these two things and we make it into a function. Well, let's try to take the derivative. So if we take the derivative, we just take the derivative of the inside. And then because there's this nice subtraction in the middle here, we can split up this derivative. And now, since both of these are antiderivatives of f of x, both of their derivatives are just going to be f of x. And therefore, when we take their difference, we get 0. So this means that the derivative h prime of x is equal to 0, but this can only happen when h of x is a constant. It's just a horizontal line, which means that the difference between these two things really is just a constant. So the question is, okay, who cares? What does this tell us? Well, what this theorem tells us is that antiderivatives and indefinite integrals are the exact same things. They're the exact same things. You find an antiderivative, you got yourself an indefinite integral. You find yourself an indefinite integral, you've got yourself an antiderivative. Same things. So here's going to be our new notation, okay? We're going to call this an antiderivative or an indefinite integral. So we're going to represent it here by the normal thing that looks like our integral symbol, but we do not have any upper or lower bounds here, okay? They're empty, and that's what makes it indefinite. But what this really means here is this really means to compute this function plus a c on the other end, where c is a constant. And so what this thing really is, this right here is just a question, or just a challenge. It says, find the function f of x so that the derivative of capital F of x equals that little f of x. Now we're going to have about 7 billion notes down here, so get ready to write quite a bit. This process of solving this type of question or challenge is called antidifferentiation. It also goes by the name indefinite integration. The constant c you see there is called the constant of integration. This is incredibly important. Do not forget to put the constant of integration at the end when you solve a problem. We'll see some examples, and it's very, very important to do this. So the whole family of functions represented by f of x plus c is called the general antiderivative of f. It is also called the general solution to the differential equation dy over dx equals f of x. So this is sort of a different way to present the same problem, and we'll show some examples of that in a little bit. But this is called the general family. And a differential equation in x and y is just an equation that involves x, y's, and the derivatives. Once again, like I said, we'll talk about this in a little bit. Now, a few more key features to always think about when working with integrals is, first of all, that if you see an upper and lower bound that are numbers, that thing's just going to be a number, okay? That's not a function. Also, this thing, like that, really is a function with an undetermined constant c, okay? So it really is a function, and it really does have a value that you need to figure out before you can use it to do anything useful. So now we want to talk a little bit about how you might see different problems represented. They're going to call on you to find this antiderivative or this indefinite integral. So the first example would just say, find the antiderivative of f of x equals 2. And so of course what this means is, you need to find, this mystery function here, and you want to find it so that when you take its derivative, you get yourself 2. So, we think, and we think, and we think, and we think, how are we going to do this? And hopefully what you remember is well, I know that the antiderivative of 2 is going to be the function so that when I take its derivative, I just get 2. And so I need 2x, because when I take the derivative of 2 times x, I'm left with just 2 by the power rule, right? That 1 comes down in front, but 1 minus 1 leaves me with x to the 0, so I just get 2, and then I'm going to put that plus c on the end. Ooh, constant of integration, so nice to look at. And so this is my solution to my problem. I have found here a function so that when I take its derivative, I get myself 2. So I've solved the problem. Now, of course, it doesn't always hurt to check your work and just take the derivative real quick. Well, the derivative, let's see, 2x plus c is going to be, 2 plus 0, so 2. Good job. Now, another problem might say to you, instead, find the antiderivative, g of x of f of x equals 2, so that g of 0 equals 1. Well, from our work in the previous problem, what we know is that g of x equals 2x plus c is certainly an antiderivative. The problem is it's this pesky c here, right? If we tried to put 0 into g right now, we'd get g of 0 equals 2 times 0 plus c. Well, we want that to equal 1. This is what we want to have happen, but it's not true yet, unless we make c equal 1. Because then what we have is, we have the new function g of x is equal to 2x plus 1, and g of 0 equals 2 times 0 plus 1 is equal to 1. So that tells me that this is the function that fits the two properties. It's an antiderivative of 2 and g of 0 equals 1. So since it fits both parts, it works really well. Now another way you might see the problem presented before says to solve the differential equation dy over dx equals 2 with y of 0 equals 1. This is actually the exact same problem, it's just presented a little differently. And here we have a nice example of what's called a differential equation. Over here we have a derivative, and over here we have a nice expression. And so what this is this is a nice differential equation. And what you want to do when you look at these things is you want to think, well, I need to integrate. So what you do is the first step is you write this like dy equals 2 dx. It's okay to separate them. And then what we're going to do is we're going to integrate both sides. Because integrating both sides now says, well, in this case, the thing to remember is that there's a secret 1 on the left-hand side there. And so what this means is I want to find the function with respect to my variable integration of y, so when I take its derivative, I get 1. And so on the left-hand side, we're going to end up with just y. And the reason for this is because if we take the derivative with respect to y of y, we get 1 and it matches. On the right side, well, we've done this one before. This is going to be 2x, because when I take the derivative of 2x, I just get 2. And here you might think you're done, but we've forgotten something. We've forgotten that what we really need on both sides is a constant of integration. Okay, so these are just different constants, but it's okay. And what we can do is we can bring them both to the same side. So we can have y is equal to 2x plus e minus d. And what we're actually going to do is we're actually going to combine that into a single new constant. So what happened is I took the e minus the d. They're just numbers. When I subtract two numbers, I get a number. I'm going to call it c because that's convenient. And so just like before, I have this function here that solves my differential equation because it's an antiderivative of 2. But I haven't finished the problem yet. I still need to make sure that when I put 0 in here for x, I get 1. So down here I can say, well, let's see, y of 0, I really want it to be 1. 2 times 0 plus c. And so after simplifying down, what this means is 1 has to equal c. So I end up with a final solution, y of x is equal to 2x plus 1. So these things can have different forms, but they're just going to be all about finding these antiderivatives and maybe figuring out a c that works. Now here we have our big list of differentiation formulas. We've looked at all of the derivatives on the left there. And correspondingly on the right, what we've got is we've got all the integration formulas. So for example here, we've got that the derivative of a constant is equal to 0, which means that the integral of 0 is just some constant. We've got that we can take a constant and move it out of the derivative. Same thing with the integrals. We can separate sums of derivatives. We can separate sums and differences of integrals. But the key rules we want to look at are the ones below. So first we want to look at here is our friend the power rule. So our power rule said that if we took the derivative of x to the n, we're going to take n times x to the n minus 1. And what the integral formula says is that we have to do this sort of in reverse. We have to instead raise it to a power, and then what we need to do is we need to divide by that new power. So let's look at what this means with an actual example. So suppose I wanted to integrate x cubed dx. The first thing to recognize is that in this case my n is equal to 3. So this means if I just look at it in terms of pushing symbols around, I need to take x to the 3 plus 1 all over 3 plus 1 plus c, because when I simplify this I get x to the 4th over 4 plus c. Now the reason this works is because remember that this over here means I need to find the function, so its derivative is x cubed. So let's check this. If I take the derivative of x to the 4th over 4 plus c, well, let's see what I get. Let's see, I can break this up into two integrals. 1/4 the derivative of x to the fourth plus the derivative of a constant. And now what happens here? Well, in this case, I'm going to get 1/4 of 4x cubed plus 0 simplifies down to x cubed. So I did get a correct answer. I just have to remember that instead of bringing the power down and subtracting 1, I have to add 1 to the power in the exponent and divide by it so that they'll cancel in the end. So the way some students like to think about this is that for derivatives, it's going to bring the exponent down. You know, D for derivative says bring that exponent down in front, whereas integrals say I need to increase the exponent. I think the best way to do it is to do them a lot until it becomes very natural for you. You're going to see the integral symbol and you're going to think this formula, whereas when you see derivatives, you'll think that formula. One last word of caution in terms of these formulas are the trig theorems. So remember before, the derivative of sine is cosine, the derivative of cosine is negative sine, so that means when we integrate we need to be careful. So here, since we went from the derivative of sine is cosine, this means the integral of cosine will be sine because integrals reverse the derivative process. And this means that since the derivative of cosine is negative sine, the integral of sine needs to be negative cosine. So the reason this works is because the integral of negative sine of x dx is equal to cosine of x plus a constant. So if we multiply both sides by -1, what we end up with is the integral of sine of x dx has to equal the negative cosine of x plus some constant. And so that's where the negative signs come from. Alright folks, you've made it. I apologize for the super long video, but it's important because here we are at the end now, able to actually work through a few example problems that you're going to face. So let's look at a couple. So I know we're starting with question number 2. Don't worry about question number 1. It wasn't that impressive. So this question is asking us to find a function whose derivative is 3x plus 4x squared, right? So this is what we want to find. We want to find ourselves a nice little function f of x, so that when we take its derivative, we get 3x plus 4x squared. Alright, so let's try to do this. So the first thing we might want to do here is we might want to break it up into two separate indefinite integrals. Next, let's bring those constants out so that we're just looking at pretty simple things inside of our integrals. And well, let's see. 3 times the antiderivative of x. So what function do I know that when I take its derivative I get x? Also, just using my good friend the power rule here with n equals 1, I've got myself 3 times x squared over 2 plus a constant plus 4, using my good old friend the power rule, x cubed over 3 plus another constant. So let's call this guy C1. And so what's usually standard is what we do is we just combine those constants into one giant constant at the end. So I've got 3/2 x squared plus 3c plus 4/3 x cubed plus 4c1. And then 3c is just a number, it's a constant. 4c1 is just a number, it's a constant. So for a final answer, I'm going to get 3/2 x squared plus 4/3 x cubed plus some new constant d. Now, many people will feel immediately comfortable sort of going through this a bit faster. They're going to jump pretty quickly through them, and that's okay as long as you don't make mistakes. Remember, it's hard to give partial credit if you made a mistake along the way, so I would show a bit of work here at the beginning just to make sure you know what you're doing. Just to make sure you get all that credit that you can, because it's much better to take your time and do it right than to go fast and get a 0. So when looking at this integral here, and I encourage you to pause the video and try to take a shot at it, what you might be thinking is, I can't actually compute this integral. We don't have simple rules. We don't have rules for products of things. I can't break this up. You know, this is definitely not equal to the integral of each one of these things times each other, right? We don't have a product rule. We can only break up sums and differences, so maybe I'm stuck. But what we need to do is we need to remember our good old friend rewrite. And what our good friend rewrite says is actually what we can do is we can say that this is going to be equal to the integral, and now we just need to multiply things out. So we're going to get 3x squared plus 3x minus 2x minus 2. And now this is something we can take the integral of, because we just need to break this up now into a few separate integrals. Actually, I'm going to simplify first, because it's going to make my life easier if I have one less integral to do. Okay, so now I break them up. So I can break this up into 3 times the integral of x squared dx plus the integral of x dx minus 2 times the integral of 1 dx. So this was a matter of taking out my constants out front for each of these, and remembering there's a nice little 1 still in there. And now I can take the integrals of these using my power rules. So this will be 3 times x cubed over 3 plus x squared over 2, using the power rule again, minus 2x. And now what usually happens is here at the end we throw a constant in at the end there. So this is sort of the idea of just leaving it to the very end, but remembering that each of these integrals has a constant, but we'll just lump them all there together at the end. And for those in the room who love simplifying, x cubed plus x squared over 2 minus 2x plus c. Well, I guess there wasn't much simplifying. But not so bad. We just got to remember, rewrite. So as always, please post a question. Try the few example problems. I've only given you a couple today because I know this was a pretty long video. And I'll see you tomorrow in class. Thanks. Oh, and don't forget about the quiz about the video. Sorry. Well, I'm not sorry. It's a good quiz. I like it.